Okay, welcome. This is the online version of the lesson for 12.1 for Calculus 3. This is Mr. Felling, and I'm going to record these. I'm trying to always record these in a way where we're not recording students. Some cases, like in this case, I'm going to pre-record the lesson so that it's available if I need to post it for someone. So I'll try to start each lesson like this by showing the screen that I usually display at the beginning of class, which contains the learning targets for the day. For 12.1, basically the idea is chapter 12 is about 3D coordinate systems and vectors and geometry of space. So we're going to talk about how to sketch points, lines, and simple shapes in 2 dimensions and 3 dimensions. We're going to talk about how to recognize and work with different sorts of equations of lines, circles, spheres, and cylinders in both 2 and 3 dimensions. And then we'll learn how to calculate distances or midpoints between 2 points in 2 and 3 dimensions. So this is actually sounds like a lot, but actually this is a pretty short lesson. Some of these lessons will be shorter, some will be longer, but I'll always try to make this as concise as possible. Homework is in our textbook, and it'll be in section 12.1. You can get the assignment also on Schoology or the Mr. Felling site. And since we don't have textbooks, I have scans of homework pages available in the weekly schedule and the materials section in Schoology. Okay, so copyrighted material is only in Schoology, so look there first. All right, I'm going to switch to the presentation then, and we'll get going here. Okay, so now here's the presentation for 12.1. And this is about 3D coordinate systems. So to start, what makes this Calc 3 is that we're working with 3 or more variables. Normal functions have 1 input variable or 1 output variable, and calculus that we've studied so far in Calc 1 and Calc 2, all the functions were single variable functions. In other words, 1 input x, 1 output y. Right? But what makes this Calc 3 is that we have multiple variables either as inputs or as outputs or as both. So we need a way to represent either the domain of the inputs or the domain of the outputs or both in more than 2 dimensions. This sounds complicated, but as we get into it, you're going to find that it's really not that bad. A couple of notation conventions. So first of all, in 2 dimensions, we also represent that sometimes as this little r with an extra line on it, kind of a weird looking r squared. That r stands for the real number system, and r squared means we have 2 dimensions of real numbers. In other words, x is all real numbers and y is all real numbers, and the 2-dimensional like space is a 2-dimensional region of 2 variables, right? So if you want to specify a position in that 2-dimensional space, R2 we sometimes call this, then you have to specify its x and y coordinate. In 3 dimensions, which would be labeled R3, we would have to specify, now we have 3 dimensions, an x, a y, and a z, and so any position would have to be specified the x, the y, and the z in what's called a coordinate triple. Right? And these things are always listed in alphabetical order from lower to higher, so x, then y, then z. Now when we draw this in 3 dimensions, there's a convention for representing a 3-dimensional space on a 2-dimensional piece of paper, and that is to use something called the right-hand rule. That if you were to put your first finger, your pointer finger, in the x direction, and then your middle finger at right angles to that in the y direction, then your thumb would be pointing in the positive z direction, right? So the coordinate systems that we're going to work with that are 3 dimensions follow this rule called the right-hand rule. And for drawing it, because in 2 dimensions we're used to the idea that the input is the horizontal variable x and the output is the vertical variable, we go ahead and make it so that the output z is the vertical variable, and then we have y be to the right, and then x really comes out of the page, but to indicate that it's coming out of the page, we draw it downward in the kind of downward and left direction like this, right? So this is really supposed to be out of the page, but it's representing that by kind of tilting downward. Okay, so it looks 3-dimensional, and that's our convention, and I'll use that convention throughout the whole course, and this is the same convention that the textbook uses. Okay, so in 2 dimensions, we have 4 quadrants, right, where the variables are either positive or negative. We start, if you can think of it as kind of going around this way, like where trig identity or trig angles are defined. Quadrant 1, quadrant 2, quadrant 3, quadrant 4 represented with Roman numerals. So in 3-dimensional space, we have 4 octants, right? So it's the same idea, except with all the positive z's first, like this. That's octant 1, 2, 3, and 4, and then another copy down below where the z is negative, octant 5, 6, 7, and 8. So we have 8 octants instead of 4 quadrants. And they are also represented by Roman numerals. Okay, so let's talk about equations and what they represent. So we know in 2 dimensions, if we have an equation of the form y equals mx plus b, or just that there's a term with x nothing squared, a term with y nothing squared, and potentially a constant term, that represents a line, like x plus 2y equals 4 is a line, right? So if we have that same equation, but we add a third variable, so like an x term, a y term, and a z term and a number, nothing squared, like x plus 2y plus 3z equals 4, that forms a plane in 3 dimensions. Everything is moving linearly, right? And interestingly, if you have an equation, say like this, x plus 3z equals 4, where there is no y variable, if we know we're operating in 3-dimensional space, that's still a plane in 3-dimensional space. It just means that y hasn't been specified. So it's like the equation it's like the equation x plus 3z equals 4 on the xz plane, and then it's just extended forever in the y direction. So you could just think of it as this 2-dimensional equation is just being stretched in the y direction to form the plane. Okay, so you have to be cognizant of whether you're working in 2D or 3D, right? Because that makes a difference. You can't just rely on how many terms there are. Okay, so if everything is linear, there's no squares, then we're dealing with a plane. If we have terms where we have an x squared term and a y squared term in 2 dimensions, then that forms a circle, right? And then the term out here is the radius squared, right? If we were to add a z onto that, a z squared term, so we have an x squared term, a y squared term, a z squared term, then that forms a sphere, which is a 3-dimensional version of a circle, right? And of course, this center here, HK, is represented here. So if you had something like this was at 2, 3, right? This would be the equation in 2 dimensions. This would be the equation x minus 2 squared plus y minus 3 squared equals whatever the radius squared is. Let's say it's 2, therefore it would be 4. Same thing here, except we just have another term, right? And the center are these coordinates right here, always with the minus sign. Okay, so what if we had an equation that looked like a circle, like x minus h squared plus y minus k squared plus r squared, but we knew we were working in 3-dimensional space? What would that be? Well, that would therefore be a cylinder. So let's say that I've defined a term for x squared and y squared, but z can be anything. And there is a z because we know we're in 3-dimensional space. If z can be anything, then that's just a circle on the xy plane like this, but it's extruded upward for all z's, right? So when you do that, you get what's called a right circular cylinder, right? So again, we have to know whether this equation is in 2D or 3D. In 2D, it's a circle. In 3D, that same equation would become a cylinder. And it depends on which one is missing. Whichever one term is missing, that's the long side of the straight side of the cylinder. So in this case, y is missing. So this is being extruded in the y direction. In this case, x is missing. Okay? Okay. So we know there's a distance formula to quickly calculate the distance between 2 points in 2-dimensional space, right? You can actually it's really just like the Pythagorean theorem, right? This distance down here is x2 minus x1, and this distance here is y2 minus y1. And so it's just the distance squared is equal to this squared plus this squared. So therefore, the distance between the two is the square root of the sum of the distances, right? And we also can figure out where the midpoint is by taking the average x and the average y, by adding up the averages and dividing by 2, adding up the two y's and dividing by 2. So in 3D, there's a 3D version of this. We just add on another term for the z, Okay, and actually all of these things we've talked about so far are extendable into dimensions above 3D. So if you have 4 dimensions or 5 dimensions, of course, once we get above 3, it becomes impossible for us to really picture it because we're living in a 3-dimensional space. So, and certainly difficult to draw on a screen. Right, so we'll tend to stick to 3 dimensions in this class, but most everything we're talking about here is extendable into multiple dimensions beyond that. Okay, so let's see. We know that this is a circle. We know this is a sphere. One thing we might be asked is, we'll be given an equation and we'll be asked to show that it represents a sphere and find its center and radius. So in order to do that, we would have to take this equation and then we would have to force it to be in one of these forms. Now I can see already that there's an x squared, a y squared, and a z squared term. There's also x's and y's. So we're going to try to make it look like this equation up here, right? Put it in this form so that I can read by inspection where the center and radius and what the radius is. So let's go ahead and do that. The way we're going to do that is we're going to group the like terms and complete the square. So hopefully you're familiar with that. I'm going to use one tactic that I use for completing the square. If you know another tactic, that's okay too. But here's the way I would approach this problem. So I would say, all right, let's group all the x terms together. So I've got 4x squared, and then I'm going to move this 8x to the other side, so minus 8x, and then I've got a 4y squared plus a 16y, right? And then I've got a plus 4z squared, and then that's equal to 0 because I moved this over. So we're going to try to force this to be in the form a number times a quantity x minus something squared. So the first thing I'm going to do is I'm going to factor out the 4 that's in common. Right? So we'd have x squared minus 2x. I'm going to leave a little space there. Okay. Same thing here. I'm going to factor a 4 out here, and I'll have y squared plus 4y. Right? And then here I'll just factor a 4 out, and right now I just have z squared. Okay. Equals 0. So now my goal is to try to turn this into this form, 4 times x minus something squared plus that same 4 here, this 4, and then we have y minus something, so y minus something squared, and then 4z minus something. Now this z is just z, so I can go ahead and write that right now as z minus 0 squared equals 0. Okay, now here's what I'm going to do. I'm going to switch colors and show you the steps that I use to complete the square. So the idea is, we know that this number that goes here is this number with its sign cut in half. So if this is a minus 2, this will be a negative 1, and then that squared has to be placed up here, so plus 1. But because I added that 1, it's being multiplied by 4. I really unbalanced this equation by adding 4 on this side. So I have to add 4 on this side to compensate. And I'm going to do the same thing with this term, because this is not yet in the right form. So if I take this plus 4 here, cut it in half, I get minus 2. Negative 2 squared is positive 4, right? So I'll add it in up there. That way this term and this parentheses term are exactly identical, just written in 2 different ways. But 4 times 4 is 16. I unbalance the equation by adding 16 over here. I have to add 16 over here as well. And so right now I have this is actually equal to 20 over here. Okay. So to do the one final step, I'm going to, if I can, I'm going to divide out these numbers. Now, if these numbers were not all the same, it means we would be having an equation of an ellipse. But because we have, and it would be what we call, we'll study this later, an elliptical paraboloid, or an elliptoid, sorry, an elliptoid. But for now, these are the same, so I could divide everything here by 4, and that would give me x minus 1 squared plus y minus 2 squared plus z minus 0 squared equals 5. Okay, so now I know by inspection that this is a sphere, right? And the center of the sphere is at 1, 2, 0. And the radius of the sphere is the square root of 5, because that number out there is r squared. All right, so that's it for section 12.1, and your homework for tonight will only deal with those. Leave that on the screen a little longer. We'll move on to the idea of a vector tomorrow, and the course will just steadily ramp up in terms of difficulty. So I feel like it's nice general introduction, and that's a good thing. All right, if you have questions, if you are learning this online because you were unable to attend the meetings, first of all, I would encourage you to attend the meetings because other things happen besides the lesson. We do interaction, we do homework questions. There will be times you have to attend because we have quizzes and things like that happen. But if you're unable to attend for some emergency situation or something and you're learning it this way, you can still get homework questions answered by attending the next session, because we'll be going over questions the next day. Or I have my office hour tutoring sessions 30 minutes before and after school at the normal link. All right, that's it for 12.1. Thanks.